every single innings played in one internationals up to a certain point in time, and we have all of these statistics related to that. Let's see what we get if we play with that. Firstly, let's answer the question, which country's players score more per match, which is simply taking the country and the number of runs and doing an average on that. Any guesses?
Australia.
Australia, South Africa,
India.
India,
I think it's Sri Lanka.
Sri Lanka. South Africa and Australia, then they are on top, followed by India. Sri Lanka, not quite there. You can flip this question and say, which countries do high scores get scored against?
India.
Yeah, obviously, I mean, Hong Kong is
Yeah.
India is the highest in the.
Among the
well-known ones.
which is an interesting one then to do, which is to say, look, there are countries that score against other countries, there are countries that get scored against. So, what can we do about that? Let's do a scatter plot in a few minutes.
Afghanistan.
That should be to
Yeah, so
India
nobody.
playing lots of home matches.
That's another contributing factor. So we want to see away versus home is something else to look at. But since you mentioned Afghanistan, notice that very few people, very few countries, very few players have scored lots of runs against Afghanistan. My guess is not because they couldn't, but because they didn't need to. That's my guess.
So you could look at batting first versus
Yeah.
batting second.
That's the other thing to look at. But the usual suspects are right there. Australia, very tough to score against. West Indies, South Africa, Pakistan, England. Not India's not quite in the same league. So let's do this analysis. What's this marks? Skip it. This okay. Let's do a pivot table in which we take the country and we take the runs, we make that an average. So that gives us the average number of runs that they've scored. I'm going to just take this and put it on another sheet. And so this country, runs scored, and let's now change this to the country against which you are playing. So versus, and in order to put these onto the same table, I'm going to use VLOOKUP. So against look up the country in this table and just get me the second value. Now let's plot these as a scatter plot. Okay, so the horizontal axis is the number of runs the country has scored. The vertical axis is the number of runs scored against them. So somebody here scores a lot of runs and has very few runs scored against them. Somebody here scores very few runs and has a lot of runs scored against them. And by and large, it goes linearly. These two countries, fairly easy to guess.
Australia, South Africa.
Australia and South Africa score the most heavily scored against them. This country, which is almost there, scores a lot of runs, but also has a lot of runs scored against them. India. The other one that's sort of above this curve, that scores a reasonable number of runs, probably has more runs than is normal scored against them, is Zimbabwe. I don't remember what this was. Let's see. This is a country that scored 20 and 19. Let's see what we can find 20 and 19. Unfortunately, Excel's scatter plots are in data for Afghanistan. So, not scoring a reasonable number of runs, but not having that many runs scored against them, which is interesting. Which means that their players, on average, are scoring a reasonable number of runs, but their opposition tends not to have to score that many runs against them. No idea why. Look at Afghanistan's matches.
This is for how many matches? I mean,
For every single, let's find that out. There is a match ID. No, this is the match ID. I got the URL. So let's. So the total number of matches is about 3,200 matches played since the history, ever since one internationals began in history, till roughly end of last year.
And then you have to see how many each of them play.
Yeah, so Afghanistan would have played much.
yeah, the B column B
Yeah.
shows the number of,
The average number of runs scored by all players.
column B is the runs and the number of matches that each country plays, we don't.
That hasn't come through so far. So let's just add that as a column. If we say how many matches have been played against them, so this will be here. You get a count. And Afghanistan, 167 matches. That's not too small.
Yeah.
That's reasonable.
Exactly, yeah.
Compared to
It's
East
more
Africa.
than 35. which
How
is
is
small.
No, is that 167 innings? See, because
No, that's 167 players who played. That's not 167 innings. But still, it's not too small a number. I mean,
But which other countries have played against that also?
which other countries is also a factor. So maybe they've been playing only against worse companies. It's not just in terms of which are the maximum wicket playing countries. Afghanistan is in the bottom half, but not so close to the bottom as to be ignored. So that's a thought. What else can we see? Let's do this weekday, day of the year, day of the month thing again. Okay. So if we take the average number of runs scored on any weekday and the average strike rate on any weekday, that's the pattern. So looks like Mondays and Wednesdays aren't good from a runs average perspective. Wednesdays are particularly bad from a strike rate perspective.
Wednesday is bad for everyone.
Generally is bad.
Wednesday seems generally bad, yeah. Monday seems relatively poor. Now in all of this, we've been looking at averages. We haven't been looking at how significant that average is. Now can we conclude that just because there is a 0.1 or 0.2 difference, is that really meaningful? There will always be differences. You will always get a colorful pattern like this when you do conditional formatting, and you will always see some quantitative difference. But is that meaningful? So can we determine the significance of each of these is the other question. That's what we're going to spend the second half of this class on. Supposing the boys' marks in the Karnataka marks distribution were distributed like this. So this is just made up data like this. Let's say most of them scored between around 35 to 45 marks. That was their marks distribution. Let's say that was the girls' marks distribution. Somewhere between 55 and 65 is where most of them are. There will always be a few boys that sort of go down here and score very high. In fact, the topper could be a boy. Similarly, it could be a girl that's scoring the lowest marks. That's always fine, but it's by and large in this range. And looking at this, you'd say that there's a fairly high probability that the averages are different. There's a good chance that girls are scoring higher than boys because the difference in the averages is much higher compared to the spreads. So that's a reasonable conclusion. But if your data look like this, probably say there's more of an overlap. Maybe I'm slightly less confident about the result than I was with the earlier one. And the data was like this, I'd be a lot less confident. Now, associated with almost every statistical test is also the probability that it could be right or wrong. Almost every comparison that you do, you can say, what is the likelihood, what is the numerical likelihood that this is right or wrong? So, a comparison of averages uses in statistics what is called the t-test. It's just the name of the test. Now the reason why knowing the names of tests is important is because most packages that help you compare these and get the probabilities will use these terminologies. The reason you need to know is just to know what to look for. Even in Excel, Excel performs a t-test. I'm going to show you a t-test on Excel. But you'll need to know that that's where I need to go to figure it out. So remember a few of the words that I'll be tossing. For all of today's examples, the only test that you need to know is called the t-test. Now, the t-test will give us a probability. Interpreting this probability, if the probability is high or is low, it means different things. Now, without knowing what the test does, it's difficult to figure out what the probability means. The rule of thumb that I've come to adopt is that for the vast majority of the tests, the lower the probability, the more interesting the result. This is not true in every case. It is true for the vast majority of the cases that I've used. So 99.5 or 99.9% of the tests that I've done, a low probability indicates an interesting result. Now, at this point I'm going to go into statistics. Don't panic. There's this book called The Hitchhiker's Guide to the Galaxy. It said that, and this is a quote from the book, despite its many glaring and occasionally fatal inaccuracies, The Hitchhiker's Guide to the Galaxy itself has outsold the Encyclopedia Galactica because it's slightly cheaper and because it has the words "Don't Panic" in large friendly letters on the cover.
Carrying the car.
What's interesting about this book, The Hitchhiker's Guide to the Galaxy, is that it's a real book which talks about a fictitious book called The Hitchhiker's Guide to the Galaxy. Apparently referential. But more to the point, I do want to mention Cooper's law. It says that if you do not understand a particular word in a piece of technical writing, ignore it. The piece will make perfect sense without it. As I go through stuff here, if there's anything that makes no sense to you, please do not worry. Ignore it. What I tell you will make perfect sense without it. So, what we're going to do is take this data set and I'm going to walk you through how one performs a t-test in Excel. So let's say I have a column that contains the strike rates for every single match played on Tuesday, and a column that contains the strike rate of every single match that's played on Wednesday. And my question is, are Wednesdays substantially worse than Tuesdays? We know Wednesdays are worse. If you go back to the table above, we know that strike rates on Wednesdays are averaging 64 and strike rates on Tuesdays are averaging 67. So we know that Wednesdays are worse on average. The question is, what is the probability that this is significant? On Excel, here's what we do. We go to data, get to the data analysis toolbar, click on that and it'll open up a menu like this. Many of you, if you haven't used it before, will not find the data analysis toolbar. It is available in Excel, but you have to do a bit of digging around to enable it. So do a Google search, spend some time figuring out how you enable it and then enable it, because it varies from version to version of Excel, and because I enable it every time I install it on my machine, I really have no idea. Again, if you ask me how to enable it, I don't know. I'll have to do a Google search myself.
But you have Excel Stat which does the same thing.
Excel Stat does this as well. There are a number of other packages that do the same thing. Just give you one example that if you have Excel is already installed. I'll also show you how to do this in Python. In fact, in Python it's slightly easier. What this will show you is a set of analysis tools that you can use. And because we're going to do the t-test, we're going to pick one of these. Now there are three kinds of t-tests that Excel will show you. What we are going to do is a t-test for two samples assuming equal variances. Now this is where Cooper's law comes in. Okay. Let me tell you what matters. It matters that you're doing the t-test. Try all three of these with the kind of data volumes you have. It will make no difference. You'll get the same conclusion. The actual numbers that you get for the probability may be 1.5 into 10 power minus 5 versus 1.7 into 10 power minus 5. It doesn't matter. It's 10 power minus 5 into something. So that is what you need to remember. What you don't need to worry about is what I'm going to tell you now, which is how these tests are different. If I have two samples, they could be different in their means, which is obviously what we are trying to test. But they could also be different in their variances. So one could be wider, one could be thinner. Now, if you know beforehand that these are expected to have the same spread, then you do a test assuming equal variances. If you know beforehand that they have different variances, or if you know beforehand that they have different variances, then you do the test of using unequal variances. Now, how do you find out if they have equal variances or not? There is something called an F-test for that. But I'm not going to worry about the F-test right now, because I'm not interested in whether these have same variances or different variances. And the result of the test, assuming equal variances and assuming unequal variances, are going to be practically identical. So let's see what we get with that test. So when you select this t-test, two samples, equal variances or unequal variances, and click OK. The unequal variances thing that is below the floor. The next screen that you get will ask you to enter the range for variable 1. So that's the Tuesday column and the Wednesday column. You can ignore the rest and just click OK. Just fill in the two columns. Now each of the others have a significance, but other than the tick mark on labels, which says that the first row has a label, you don't really need to worry about any of those. And this is what it tells you. Cooper's law again. Ignore what you don't need. Now the only thing out of all of this that we need is a probability. Okay. And probabilities are usually depicted by a P. And there's this P one-tailed, P two-tailed. It doesn't matter which one you pick, but I'm going to pick the two-tailed one. So that is the only number that we're concerned about. So this says that the probability that these two are different, actually the probability that these two are the same, the variances don't have a difference, is 1.4 into 10 to the minus 5. So that's 0.00014. 0.0000014, which is very small, meaning that these are almost certainly different. It's saying that the probability that Tuesday and Wednesday have the same strike rate is 0.000014. In other words, there's no chance that Tuesdays and Wednesdays have the same strike rate. It's almost 1 in 10,000 kind of an event. Fine. Which means that there is a Tuesday versus Wednesday effect. So Wednesdays are actually worse, Tuesdays are actually better. We don't know why. Data will never tell us why unless we do another test on it. The same test in Python would look like this. You import this module called scipy.stats. You have to have installed it first, but let's assume you install it. You import this module, and then within that there's a scipy.stats.ttest_ind. Again, there are a variety of t-tests. There's a test for independent samples. Independent samples means you assume that they are unequal variances. There's a t-test_rel, which assumes something else. Doesn't matter, just pick any one at random. Pass the Tuesday rate, pass the Wednesday rate, which will be stored in an array. You would have to have created those or loaded them from somewhere. And it gives you two numbers. Fortunately, this is a little easier to interpret. The first number is the difference in the mean. So it's saying that the strike rate difference is 4. So Tuesday minus Wednesday is 4.3 strike rate. And the probability is 1.4 into 10 to the minus 5. Roughly the same number. You'll notice that the numbers don't exactly match. That's because I goofed up and taking the data set. I deleted a few rows by accident. But otherwise the numbers would more or less be the same. So it's saying the same thing. There is a difference. And that's the chance that this difference is negligible. A number really close to 0 tends to indicate an interesting result. The interesting result here is that they are different. Okay. Now, if we apply this to all of these, okay, so let's take this score rate and the runs. We compare Tuesday and Wednesday. What if we compare every plan? That's what it looks like. The probability that any given day is different from any given day is this set. Now the value here is the same thing that you got by, so the value here, for instance, on Wednesday versus Monday is the t-test probability of comparing the Wednesday strike rate versus the Monday strike rate. Remember, values close to 0 are interesting, values far away from 0 are uninteresting, but on this one it looks all like a mess, so let's make it slightly easier to see by just looking at which are the values that are closer to 0 and hiding the values that are less close to 0. So this and this look very significant. That value is 0.000 and the rest is in trailing spaces. So that's a Wednesday versus Tuesday comparison. They're just mirror images. We saw that already. What also looks interesting is the Sunday versus Wednesday comparison. So that seems like a significant result. Sunday versus Wednesday. Sunday and Wednesday definitely have different strike rates. But what is not interesting is Thursday versus Monday. Looks like on Thursdays and Mondays you have more or less the same strike rate. The actual numbers would be different, but it's not significantly different. You would, or Tuesdays or Mondays, but there's a 4% chance that it could be different. Now, 4% chance that it could be the same, which is not too bad. Now, generally, people consider 5% a good cutoff in statistics. If you got a number that's less than 5%, it's termed good. Now, that was at a time when large data was scarce. Today, you can comfortably say anything less than 1% is good, and if it's above 1%, you probably have to reject it. That is that is with scientific data of various kinds, be it social science, be it the hard sciences. With business data, it's usually tough to get that kind of precision, partly because there are too many other variables that influence it. So in business statistics, you tend to be a little more relaxed with the probability criteria. You say, if I get a probability of less than 10%, there's a chance it's worth investigating. But anywhere else, you would stick to 1% or a lot less. In fact, if I get anything less than 0.1%, that's when I start saying this is interesting, but I just ignore it all. So there's only two numbers that I do here. But now this, while it's showing what comparisons are interesting, it doesn't show us what the difference is. So let's just, instead of let's use the same color scheme, but instead show the numbers that show the difference. So for instance, what this is showing is Wednesday compared to Tuesday is minus 0.31. So Wednesday is 3.1 strike rate less than Tuesdays on average. It's saying that Saturdays are 2.63 less than Tuesdays. and that's slightly less likely. That probability there is 0.003, just still good. It's saying that Mondays are less than Tuesday by 2.53. That's a 5% chance, right? 4% chance, which is okay, not too bad. But it looks like Tuesdays are higher than all the other numbers that you see. Wednesdays are lower than all the other numbers that you see. Saturdays are lower than all the other numbers that you see. Sundays are higher than all the other numbers that you see. So the conclusion that I would draw is Sundays are pretty high, Tuesdays are pretty high, Wednesdays and Saturdays are pretty low. And these are statistically significant. Meaning that I can go to the bank with these numbers. At least Wednesday versus Tuesday, I can say for sure there is a difference across the history of one-day international cricket. We don't know why, but there is a difference. What about the average run score? We'll be looking at strike rate. Is there a difference there? That's what this table looks like. Every single probability is at least 3 digits equal to 1. Which means if we highlight only the ones that are close to 0, there's nothing that's highlighted. So while the strike rates are varying by the day of the week, the average runs per player do not vary. Take it forward as well. Now, this is something you would want to apply to every comparison of means that you do. Is this significant? Is it not significant? In all the analysis that we did earlier, boys versus girls, higher or lower, by subject, higher or lower, day of the week, whether a person is born, day of the month, when a person is born, what marks do they get? Every single one of these, or calories for instance, chocolates having higher calories versus less. In all of these cases, you can do this t-test and also come up with a conclusion that this is significant or no, it is not significant. And that's what makes the analysis more meaningful, because what you have by default is every possible combination of analysis. And this is the filter that you use to say these results are meaningful, at least from a statistical sense. Whether they are interesting or not is a second level filter that you have to apply subjectively. But that this analysis is valid is something that the numbers can throw at us directly. So here's how I would coin this whole process. Remember we spoke about automated analysis or autolysis the beginning of the class. If we were to coin the first rule of autolysis, it would probably be this. First, find all the groups and numbers. By groups, we're talking about things like categories, whether the word is present in the title or not, things you can group by. And all the numbers. And by numbers, I simply mean anything that you can take an average of. There are different kinds of numbers, and the interpretation of the averages could be different. For example, if I ask a person to rate something on a scale of 1 to 5, versus ask a child what their age is, the averages have a very different meaning. Now, for the age of a child, you can say that a 2-year-old is twice as old as a 1-year-old. You can say that a 5-year-old is 5 times as old as a 1-year-old. You cannot say that the person who gives a rating of 5 to a service likes it 5 times as much as a person who's given a rating of 1. It's a relative scale. Firstly, ratios don't play a role. It is also not a rigorous interval scale. You cannot say that a person who gives a score of 1 compared to a person who gives a score of 2, the difference between them is the same as between 4 and 5. It could be completely different. Okay. So remember that averages tend to work better when you're looking at numbers that have ratios, when the average is actually a physical number, but they don't work too bad with data like surveys either. Okay, where you have a different scale. If you take an average and that average makes logical sense to you, then you can apply this analysis, and that's what we mean by a number. Now there are many things that might not look like numbers but actually behave like numbers. Dates are examples of those. You can take an average of a date. You can also group by dates. So there are some that fall in multiple categories, and that's absolutely fine. If something falls in both categories, put it in both. Now, take every number that you got. For example, in the Tesco groceries case, we had kilojoules per 100 grams and we had the cost, the price per 100 grams. Take both numbers. For each number, take every group. So that could, in the same example, why am I doing this? I got an example. So in that example, it could be the category of the product. It could be whether the product had the word chocolate or not, whether the product had the word Tesco or not, and any other groups that you can think of. Calculate the group-wise average. Now, some of the things we found by calculating the group-wise average was that snacks have the highest calorie rate, fruits have the lowest, cakes have the highest calorie rate, breads have the lowest. Tesco products that have the word Tesco, you can do this analysis, I did. they tend to cost less but have more calories, which is sort of more value for money. You saw this with the word value. If there's value, then it costs less, but there's more calories. That is also associated with the product, with companies, with products that have the word Tesco in them. And then do the t-test and strike it out if it does not have, if it has a probability of greater than 0.01. Leave it in if it has a probability of 0.01. In this case, the same analysis, every single one of them has a probability of less than 0.01, so which means they are all statistically significant. We leave them in. But if we did the cricket analysis, take the groups, take the numbers, so for every number, that's runs and score rate, we just had two numbers. We have the country, player, match date, ground, which country you're playing against, and we've got a number of conclusions. I'll read out the last two. Tuesdays have the highest strike rate, Wednesdays have the lowest. Saturdays have the highest run score, Wednesdays are the lowest. Now out of these last two, the last but one is statistically significant. The probability of error is less than 0.01. The last one is not. The probability of error is in fact 1. So knock that off. And that can be done without any kind of logic. Just blindly apply these rules and you'll get a set of potentially interesting results. You certainly have a set of valid results and then you do the filtering. What this does is bypasses the intelligence required to do analysis. Now that we've gotten it to an algorithmic stage, it's just a matter of applying these rules. But where the intelligence now has shifted in this is in identifying the groups and numbers. Now, while it might seem relatively obvious, right? You've got a bunch of columns and you can take groups and numbers out of those. No, not quite. Not quite in the sense that that's not all you can do. You can go a lot further than this. And what I'm going to talk about is how you can create derived groups and derived numbers out of any set of data that you have. What I'm talking about from here on is more art than science, but I'm going to try and algorithmize this as much as possible. Let's start with how we extend groups. From existing data, you can always create new groups, and what you will be doing by and large is trying to find more interesting groups that you can create. I'm going to take 4 common types of data that you have groups, that you can create groups out of, and see how you can create groups out of those. Let's say you have geographic data. For example, if you had a city, if you had a country, there are a number of things you can derive out of that. Starting with a pin or zip code, for instance, you can figure out which city it is in, or town, or whatever. Which state that belongs to, which country that belongs to. So which means that you can start rolling up the analysis to a different level. It's almost like adding a new column. Given the pin code, find the city, put in the state, put in the country, and that each of those comparisons could give you potentially more meaningful results. You could also get the latitude range or longitude range. So is it, for instance, in the northern hemisphere or the southern hemisphere? Most of the countries are in the northern hemisphere. Does that make a difference? Is it, and you could take each latitude and longitude and put them into arbitrary boundaries. Effectively, a country is a collection of latitudes and longitudes. Any geographic boundary is a collection of latitudes and longitudes. So you could take that and say whether it belongs to this block, that block, any kind of geographic categorization. So that's one way of creating new groups, hopefully which will align with the problem or question that you're asking. Another is time, and we've done a bit of that. Given a time column, by which I mean date and time column, here are in descending order, I think, of the kinds of interesting analysis or interesting new columns that are created. Find out whether things are different by the day of the week. We found that strike rates differ by day of the week. We found that birth rates are lower in the US on Sundays. Find if something is different by day of the month. We found that round number dates, 10th, 15th, 20th, they tend to have more people born on that day and tend to score lower marks. And we have a sense of why it happens. You'll find that month of the year, you'll find that most, if you take any budget preparation and compare whether the actual usage of a department's budget is higher or lower than what was planned, the results will be varied, but one thing you will consistently find is that almost every December, the actual will be higher than the plan. Now, that varies from country to country. It's basically the end of the budgeting cycle. If a department finds that it hasn't used up the budgets, their biggest worry is their budget will get chopped off the next year. So there's a mad rush to make sure that that amount gets spent. That's a fairly good way of reducing budget usage, right? So at the end of the year, see which department has fully used their budget. If they fully use it, obviously they need that money. If they haven't, obviously they don't need that money. So chop off the ones, the budgets of those departments. So we did this at a pharma company and found that in December, everything just shot up beyond what it was supposed to. Hour of the day, that can be quite interesting. So for instance, we were looking at which cities using ISP data wake up early to browse versus sleep late to browse. Took Mumbai, Delhi, Chennai and Bangalore. Two of these cities were early risers, two of them were late risers. I think you should be able to easily guess. Which are early? Chennai early.
Bangalore late.
Bangalore
Mumbai.
Bangalore early.
Mumbai.
Chennai and Mumbai.
Okay, let's do one by one. Chennai early, late. Okay, that's late. Okay, it's almost consensus. Chennai is early. Bangalore early, late. Bangalore is early.
Wow.
Well, now the conclusion, the rest of the two are obvious. Mumbai and Delhi are the late ones.
What's early?
Early means they wake up anywhere between 3 a.m. to 7 a.m.
Oh my God.
They must have been stayed up the whole
Could be the BPO thing, so it's not really as much as really late.
It's probably not a very- I think category should be 5.
So, hour of the day could be interesting. Day of the year, whether it's the beginning of the year, slightly less interesting, but there are some solutions that come out of it that are weird. Week of the year, minute of the hour, and there was a call center for whom exactly between the 15th and the 20th minute, their productivity was dropping in 1%. And that was when they later on found out that chai was being served. Using text data, we've seen how we can figure out if a particular piece of text contains a string or not and use that as a category. Chocolate, value, finest, Tesco, organic. The length of the text could be interesting. The number of words in this could be interesting. There's a number of pieces of text analysis that you could go. I'm intentionally not going too deep into what you can do with text, but this actually would be a very, very, very long list of stuff that you can do with just text data. And finally, numbers can give you groups as well. You can say, let's take example, so strike rate. Is the strike rate greater than the average or less than the average? Who has the strike rate greater than 100? Now, those give you additional columns. Players who have a strike rate of over 100 versus players who have a strike rate of less than 100. Players who have above average strike rate, players who have less than average strike rate, players who have a strike rate of below 30 on average. Pick a number which has logical significance or significance to the domain and compare it with that value. Or pick a set of numbers, say 0 to 30, 30 to 70, 70 to 100 and beyond 100. Or you could find a more natural way of grouping it. Top 25% of the scorers, next 25%, next 25%, or any percentage, top 10%, next 10%, next 10%. Take students' marks, group them into quantiles. That's another way of creating categories. So top quarter, last quarter. Or you could group them into equal intervals. So this is not the top 25% of the students, but all of the marks. Students who scored 90 and above, 80 to 90, 70 to 80, which are cutoffs that are equally distributed, both of which are ways of picking values to compare against, but you're always picking multiple values. Or you could group by pretty much arbitrary number of values, not too different. What you may want to do is separate round numbers. So by separate round numbers, so we were doing an analysis of ATM withdrawals. Okay. There are two very, very clear and distinct categories of withdrawals. Those withdrawals that were multiples of 100 rupees, which is what an ATM gives you, and those withdrawals which were not, which is something that ATM does not give you. So how on earth were these people able to withdraw 739.63 rupees from an ATM? We don't know. We just got this data day before yesterday, and we're still trying to find out. It could be a foreign currency transaction, which was the case for a small fraction of them. So this was a converted amount. It could have been a point of sale transaction, but we filtered those out. But there are still a number of transactions which have a round number. We'll find that out. But that's an interesting thing to look at. The other way of looking at round numbers is to see what, so like with dates, for instance, 10, 15, 20, is there a round number? Is there something that is interesting in those? energy usage, for instance, you'll find a huge number of people whose energy usage is exactly at the slab boundaries. You find that so in AP, for instance, the energy usage, if you take a histogram of the energy usage and how many people have a usage of 1 unit, 2 units, 3 units, all the way up to how much ever it goes up to, you'll find a relatively smooth log normal kind of pattern, but there is spikes precisely at the slab boundaries. 50 units shoot up, 100 units shoots up, 200 units shoots up, 300 units shoots up. Now, either people are watching their usage very carefully and just turning off their energy usage before it goes to the next slab, or there's some money being exchanged. And it's not just money being exchanged at the slab boundaries. What also happens is the number of meter readings at 10, 20, 30, 40 are unusually high. Here there's no money being exchanged. There's no logical reason for somebody to prefer 10 units over 11 units. They may as well have gone to 11 units instead of 12 units. This is more a case where a guy is not going to check the meter in the first place, sitting in his office and just cooking up a number. So, yeah, not cut and paste, as much as just make up a number. Now, sometimes for genuine reasons, there was one colony of houses which apparently no meter readings were taken for almost 6 months, large number of houses. The guy had what looked like a